Hi guys, so welcome to another video. I wanted to make a video about something outside of the school syllabus because I feel like quite often actually in the school syllabus some of the most interesting parts of math aren't covered, and that's really a shame, I think, because this stuff isn't that hard to learn, but I think it still has a lot of beauty in it as a mathematical idea, and it's definitely still worth knowing if you're interested in finding out more about math. So today I'm going to talk about something called the fundamental theorem of arithmetic. And essentially, this is one of the most important theorems in number theory and in mathematics in general. This was a theorem discovered by, I'm pretty sure it was Euclid in ancient Greece. So this is also a very ancient theorem. Now, I'm talking about this, but what does the theorem actually state? So the theorem states that any composite number can be broken down into primes. So every single number is made out of primes, and that every single number only has a unique prime factorization. So you can have two different prime factorizations, and the order of the primes doesn't change the factorization. So, for example, 6 can be written as 2, 3, but writing that in a different order, so writing it as 3, 2, is in a different factorization, first of all. And second of all, you can't change the factorizations into any other prime numbers. Once you start getting into complex numbers and roots, it is actually possible to show that there are multiple prime factorizations, but as far as we're concerned, we haven't gone to that yet, so that doesn't exist yet. So just to make it clear, the theorem states that all numbers, we should clarify all integers. You can't say all numbers because then that would also involve some complicated stuff, such as complex numbers and irrational numbers and so on. But we don't want to get into that yet. So we can say that all integers are made up of primes each integer has a unique prime factorization. So I think a cool way to think about this idea is essentially you can think of the primes as the building blocks of numbers. So in the same way that in physics and quantum physics and chemistry, the basic blocks of life and everything around us are atoms, in the world of math and numbers, the building blocks are primes, which I think is really cool because once you start learning more about primes, you actually understand how powerful they are and how big of a role they play in mathematics, especially pure math. And also in terms of something called RSA cryptography, which I will make another video on, they're really important. And RSA cryptography is actually a technique used by lots of big agencies. I think most notably the NSA use it as a technique to encrypt their documents, and they also use it to hack your emails. Okay, so how does this work? Before proving this statement, we first have to prove a few lemmas. Okay, so first let's prove that, and actually before I get to that, what is a lemma? A lemma is kind of intermediate step to showing that what I'm saying is true. So what do we need to show? First, let's show that every single number is made out of primes. We can also actually put in another quite interesting proof here about the fact that there's an infinite number of primes. But okay, first let's prove that every single number is made out of primes, or at least every single integer is made out of primes. So let's just list our numbers. So far we're just going to start with natural numbers. So let's assume that we have a set of numbers or a set of integers in the set S. We're just going to call this set S. That doesn't stand for anything. That's just from convenience. All of which are not divisible by primes. So we have some set. It can actually be an infinite set if you'd like. So we have this set S, which has these numbers. Let's just name the smallest one n, and we can go forever. And it's defined by the fact that every single element in this set is not divisible by primes. So it can be factorized into primes. And by the way, the technique that we're going to use here is called proof by contradiction, which essentially is a technique which involves making an assumption and then showing that it's false, which must imply that the assumption was wrong. But then that actually helps us prove what we wanted to prove. So we have this set of numbers, integers which aren't divisible by primes. Now let's say that there's some element of this set, let's call it m, which is the smallest element of this set. So this is the smallest value in the set. Now we know that it's not divisible by primes, therefore that must mean that it's divisible by other composite numbers. And we know that it's not prime itself, because then it would be divisible by itself in 1 and that would make it prime. So it can't be a prime number. So we have this element of the set S, which is not divisible by primes, but then that means that it's divisible by composite numbers. But since it's the smallest element of this set, that must mean that it's also divisible by smaller numbers. Because if you have some integer, it can be divisible by numbers greater than itself. So let's say it's divisible by the composite numbers, I don't know, A and B. Now since this is the smallest element of the set, these two factors are not part of it. They're smaller than n. So A and B do not go into the set S. However, if they don't fall into the set, that must mean that they are divisible by primes, right? So let's say that A is divisible by P1 and P2, and B is divisible by P3 and P4. But then, that must mean that you can multiply P1 by P2 by P3 by P4 to get M, which is a contradiction. Because of the fact that we previously stated that M is not divisible by primes, we have just shown, however, that it actually is divisible by primes, which must mean that this set cannot exist. And therefore we have shown our assumption to be false, and have also proven that every single integer is divisible by primes, or consists of primes. Okay, so we've proven that part. Okay, so we have just shown that every single integer can be broken down into primes. And now what we're going to try to show is that every single integer can only be broken down into a single prime factorization. So let's say that we have some integer a, it's part of the set z. And actually an interesting fact of why integers are denoted as z is because the German word for counting is Zahl. So integers are basically counting numbers. But that should not be confused with natural numbers. Okay, so we've just shown that every single integer can be broken down into primes. Now, given that, let's express a as a product of its primes. Let's say p1, p2, p3, arbitrary number of primes until pi. However, we're going to use the same technique that we used before, which is proof by contradiction. We're also going to assume that it has a second prime factorization, so it doesn't have a unique prime factorization. So we're going to write that as q1, q2, q3, We don't know how many q's there are, so we're just going to denote that as qj. And note that we are not assuming that there's an equal number of primes in either factorization. Okay, so since these are both prime factorizations of A, we can make them equal to each other. So writing that out, that would be P1, P2, P3 up until Pi is equal to Q1, Q2, Q3 up until Qj. Now keep in mind that these are all primes, so they can only be divided by themselves in 1. Okay, so what do we do with this? Well, let's say that we want to try and divide out some of these primes. Let's say that there's some prime here, which is also divisible by prime here. Or I try to divide out P1. If I divide out P1, let's say I divide out also one of these primes, Q1. And they must divide each other because the primes can only be divisible by themselves in 1, right? So it's not like I have some other factor which I'm not accounting for. If I'm dividing out these two primes, they must be identical, right? Okay, so we divided out first two primes because these two primes are identical. Then we have P2, P3. And also, this might seem obvious, but keep in mind that there's also an upper limit on how large the prime itself can be. Oh, we're also assuming that it is composite, since it's made up of primes. Right, so then if we divide out another part of P, whatever that prime is, it must divide out the exact same prime on the other side. And we can actually continue this process for as long as we want. But essentially what this tells us is that since primes are divisible only by themselves in 1, by dividing out one part of the equation, we must be dividing the exact same prime from the other side. So if we continue with all these primes, however many there might be, we end up seeing that actually Pi is equal to Qj. Therefore, that means that they're equal. And actually what that means is that we have divided out the exact same primes for both sides. So that must mean that these two equations are both exactly the same, right? So essentially what we've just shown is the fact that there can only be a unique prime factorization of every single number. And the key point here to understand is the reason why that works is because as we're dividing primes from both sides, they can only divide out themselves. They can't divide any other primes. So by canceling out the primes from both sides, that must mean that we're taking the primes off that are identical to each other. And that completes the proof.